Hi everyone, you're welcome to class. Today we'll be looking at something very important, and that is velocity time graph. We'll be looking at velocity time graph. So let's write. So we're looking at our title is velocity time graph. Velocity time graph. We'll be looking at velocity time graph. Okay, now velocity time graph is another means that we use to solve equation of motion on a straight line. So we use this method also to analyze equation of motion on a straight line, and we apply those three principles. And once we're able to understand these three principles, I believe these three principles should be enough to take you through, at least to help you get the concept of using velocity time graph to solve some equations of uniformly accelerated bodies. Now we have three graphs. Number one, we have the graph illustrating a body undergoing what is called uniform acceleration. So when a body is undergoing uniform acceleration, what it simply means is that the velocity of the body is increasing in equal time interval. So let's look at this. So to illustrate that, we illustrate that with this chart. Now this is the chart of velocity time graph. This is the graph of velocity in meter per seconds, and then this is the chart of time in seconds. So velocity time graph, when I have a straight line graph like this, then we call it a velocity time graph illustrating acceleration of bodies. Alright, so it means the body starts in this present leg, it starts from rest. So at this point u is 0 meter per seconds. So at that point you see u is 0 meter per seconds, and the object increased to this level. If I trace it down here, we discover that it has attained a v, which we call a final velocity. And that final velocity, it takes a certain time interval to get that velocity. So from this velocity time graph illustrating acceleration of bodies, we can deduce equation of motion from this. You see, we have u, we have v, we have a, we have t. So the gradient of this line, which is the slope of this line, is given as a equals to change in v over t. So therefore we can now say that a equals to v minus u over t. So from this place we can now say v minus u equals to at. Then from there we can now say v equals to u plus at. So v equals to u plus at can be applied here. So that is the first velocity time graph diagram that we need to understand. So this diagram illustrates a body accelerating from rest, initial velocity u, to final velocity v, and under this time interval. So if I want to determine the distance covered by this body, the body that's accelerating from this point down here, if I want to know the distance covered by the distance covered by the body is given by the area under this graph. Look at this graph. This graph has given me a triangle, and distance covered is going to be area of triangle, which is half base multiplied by height. So when I determine half base times height, whereby from here to this point, from this point to this point is our base, and from this point to this point is our height. So this place represents our base, while this place represents our height. So that is number one concept that you must understand when talking about acceleration of bodies or velocity time graph. So let's look at number two concept. Okay, now concept number two is when a body is undergoing what we call uniform velocity. That is when the velocity of the body is constant. At this point, the body is neither accelerating nor decelerating. So at this point, acceleration of the body is 0. So let's draw the graph now. This is the graph of velocity time. So we have the v in meter per seconds, and then we have our time. We have our time in seconds. So in this case, the body is undergoing a uniform velocity. So let's say at this particular velocity v, the body maintains a uniform velocity. So if you look at this line, the line illustrates a uniform velocity. So what happened at this point is that the body is neither accelerating nor decelerating. So the body is not accelerating, the velocity is not increasing nor reducing, but the velocity is constant. So this is what we call a uniform velocity. So at this point, the object covers certain distance v, velocity v, and certain time t. So from here, so we can only determine the distance under this graph. And the distance under this graph is in form of a rectangle. And remember that area of a rectangle, which is S, is going to be V multiplied by T. In other words, we can say length times breadth. Our length is the T, our breadth is the V. And if I bring this together, making V the subject of the formula, it becomes S over T. Automatically, this has become one of the formula that we use when we are solving questions in motion, where this one is the speed. I always say velocity is displacement over time, or you can say speed is distance over time. So let's look at the number 3 diagram, or the concept that we apply when we are dealing with velocity time graph. Okay, now this third graph is a graph showing that a body is decelerating or undergoing retardation. So when a body has accelerated, undergone uniform velocity, then at a certain point the body starts to decelerate. Now the velocity time graph illustrating a body decelerating is given as this. So let's draw the chart. So this is the velocity in meter per seconds, and then this is the time t in seconds. So when the object decelerates, it means the body comes from the higher velocity and return back to rest. So at this point, the body is decelerating. It's decelerating here, and from this point we can actually determine the deceleration or the retardation of this body by determining this slope. Remember, this slope is a negative slope, and because it's a negative slope, it's coming from V and going to U. So in that case, because it's a negative slope, then we can say our deceleration A, or let me say deceleration, is going to be U minus V over T. So if I bring this one into equation of motion now, we can say U minus V equals to AT. Or let me just put it that way. But what we are saying is that if you solve this question, we can also get U equals to V plus AT. But let's deal with this. Let's deal with this one. In dealing with this one, what is going to happen is that when we solve this concept and apply it, our acceleration is going to give us a negative value. But a negative value of acceleration does not mean that the acceleration is negative actually, but the negative is showing us retardation. When you solve and acceleration gives you a negative value, it does not mean that the value is negative. It's only showing this negative sign, it's only showing the direction. So in other words, if acceleration is negative, what it means is that we are having retardation, we are having deceleration. So if acceleration is positive, the deceleration is a positive value. So that's the 3 concepts we'll be applying. So let's look at the 3 concepts again. Okay, let's look at the 3 charts again. This is the first chart, and this first chart illustrating a body that is accelerating uniformly from rest. This second chart illustrates a body that is undergoing uniform velocity, while this third chart is illustrating a body that is decelerating. So this 3 concept is what we apply. So we can decide to combine those 3 depending on the motion of the object to draw a velocity time graph, and then analyze that using this graph to solve some equations that involve uniformly accelerated bodies. So let's look at how we can apply this question by using one example. Let's look at one example and see how we can apply these 3 concepts, 3 diagram to solve a particular question now. Okay, let's look at this example now. A car starts from rest and accelerates uniformly for 5 seconds until it attains a velocity of 30 meters per second. It then travels uniformly for 15 seconds before decelerating uniformly to rest in 10 seconds. Sketch the graph of the motion. So remember, we want to sketch this graph using velocity time graph. So let's take our graph to be graph of velocity velocity time graph. So this is the graph of the velocity in meter per seconds, and this is the axis for the time. This is the time in seconds. So let's look at it. The car starts from rest. Remember, when the body accelerates from rest, there is a diagram we use to illustrate acceleration, and that is an arrow which line going up. So that is a line. So it accelerates uniformly for 5 seconds. So it means it has covered 5 seconds. So from here to here is just 5 seconds. It has covered 5 seconds. Okay, let me put it clearly so that you can see. It has covered from here to here is 5 seconds. So it's covered 5 seconds. Then until it attains a velocity, it has attained this velocity. This is the velocity it attains. You can see the way I'm doing it. This is the velocity it attains, and that velocity is 30 meters per second. So this velocity it attains is 30 meters per second. So it attains a velocity of 30 meters per second. It then travels uniformly. So remember, uniform velocity is just an horizontal line that you draw like that. So the body is neither accelerating now. It moves uniformly now for how many seconds? For 15 seconds. So you can stop just any point, but the point is from here to here is another 15 seconds. So it takes 15 seconds to get to that point. Then before decelerating to rest, remember deceleration is talking about the inverse of acceleration. So coming back to rest, and it does that in 10 seconds. So from here to here is 10 seconds. So the question is to sketch the graph. So with this diagram, we have already sketched the graph using the three concepts: the one of acceleration, the one for uniform velocity, and the one for deceleration. So by the time you have sketched this graph, you understood how to sketch the graph, then it's very easy for you to now apply it in solving questions. So the graph can be of any form. It can take any form depending on the motion of the body as illustrated here. So from there, we now proceed to now apply it, this diagram, and begin to solve some questions around it. I believe you understand this class. So next class we'll look more into more examples on velocity time graph. Kindly like this video, share this video, like this video, subscribe to this channel. I believe you understood the explanation. Kindly subscribe to this channel, like the video, turn on the notification bell so that next time when I drop the video, then you'll be able to see my class or my video online. And at the same time, you can also comment in the comment section. Now, I want to quickly say something. Now, it is important to know that the body does not necessarily need to accelerate from rest, as illustrated in this diagram you are looking at. You see, this body does not start from the origin of the graph, but it starts at a certain point, that is at certain velocity. So a body can also undergo constant acceleration by moving in this direction, as you have seen in this chart. And also, if you look at this one now, this velocity time graph illustrates a body accelerating from rest from 0. You see, it's accelerated until it reached 60 meters per second. That's the final velocity, and it does that in 20 seconds. See, from 0 to 20 under the time axis. So it covered that in 20 seconds. And after it has reached 60 meters per second, which is the final velocity, the velocity is maintained for the next 30 seconds. That is between 20 and 50. It is maintained for the next 30 seconds before the body starts undergoing constant deceleration. Now, if I want to know the total distance covered by this body, so we know the total distance covered by knowing the area under the graph. And if you look at the whole graph is a trapezium. And if you look at the trapezium, you see the base is the parallel, the A and B are the parallel lines, the parallel side. So the base, we have the B is 80, you see, from 0 to 80, that's the total time. And when you look at the A is from 20 to 50, that is a 30. While the height is the perpendicular distance between the two parallel lines, which is our height, to be 60. And if you want to look at the area of a trapezium, the area of a trapezium is given as half into bracket A plus B close bracket H. as seen is this next chart. You see that is the formula for finding area of a trapezium. So by calculating area of a trapezium, we are calculating the total distance covered by the body undergoing this kind of motion. So as seen in this chart, you see that the distance covered has been calculated to be 3,300 meter. All right. And it's also important to know that the graph can also take any form as shown below. So you see, it can take any form like this. The body first accelerated, then undergo constant velocity, then before it accelerates again, and then finally go back to rest. So it is also the same trig diagrams that we've initially explained that we use in order to draw this chart and diagram. Now we can also have other types of graph. Other types of graph is, if you look at this one, we have the blue line, we have the red line. The blue line means that acceleration increases with increase in time. So at this point, we don't have what we call uniform acceleration, but acceleration is increasing as time increasing. And if we look at the second red line, what we have there is that acceleration is decreasing with increase in time. We can also have these two. There are other charts that we can also have. Look at the straight line chart. That's what we have been discussing before, uniform acceleration. And also a body can also have what we call non-uniform acceleration. You see that this one, there is a little curve. It's not a straight line like in the case of the uniform acceleration. So we can have a graph like that as well. And look at the series of graph. We can also have, you see the graph of constant velocity, constant acceleration. This one is not starting from rest. You see constant retardation. Then we have an object thrown up. When an object is thrown up, we are going to have this graph because the object has to go up and come down. So we have the positive acceleration, then we have the negative acceleration. But that one is acceleration due to gravity anyway. Then we see when the body bounces also, you have another graph like that. And when the body is performing irregular motion, we can also have that chart. So we can also have different type of chart. But primarily we use the three charts that I explained earlier to analyze motion of accelerated bodies. So in the next video, we shall be looking into how to apply that velocity time graph to solve motion of accelerated bodies. We solve more examples as time goes on. All right, thanks for watching this video. Please kindly like this video, subscribe to this channel, and turn on the notification bell. Thanks, and God bless you.